Hello everyone, hope you are doing very well. So today we are going to discuss the exemplar questions of our chapter Haloalkanes and Haloarenes. So let's begin our today's topic NCERT chapter 6 Haloalkanes and Haloarenes exemplar questions 4, 6, 9, 13, 17, 25, 30, 33 and 34. So these are the specific questions we are going to cover today because they are covering or they are containing the major concepts from this chapter. This is disclaimer. So let's begin with our first question, the exemplar question number 4. Question is, toluene reacts with halogen in presence of iron plus 3 chloride, giving ortho and para halogen compounds. The reaction is, so you have given a reaction that when toluene reacts with halogen in presence of iron chloride as a catalyst, we will get ortho and para substituted halogen compounds as our products. Then this reaction is of which kind? This you have to tell. The options are electrophilic elimination reaction, electrophilic substitution reaction, free radical addition reaction, or nucleophilic substitution reaction. So this question's correct answer is option B, that electrophilic substitution reaction. So how is it is electrophilic substitution reaction? Toluene is basically benzene ring connecting with the methyl group, right? So when it reacts with the halogen in presence of iron chloride as a catalyst, it will give us ortho and para substituted halogen compounds, and the reaction is electrophilic substitution reaction. In this reaction, the chlorine positive act as an electrophile which is going to attack on our electron rich benzene ring, and the hydrogen ion, that is H positive, was substituted by the Cl positive electrophile. Formation of electrophile. So let's see that how actually that Cl positive as an electrophile is forming. So Cl2, that is chlorine molecule. So when toluene reacts with halogen, right? So we have reactant as a halogen molecule here, which is a chlorine molecule. So when chlorine molecule reacts with our catalyst iron plus 3 chloride, that is FeCl3, you will get FeCl4 negative plus Cl positive, that is an electrophile. Okay, so this is how the electrophile forms in this reaction. Now, the mechanism of this reaction includes 3 steps. The first step is the formation of electrophile, that is Cl positive from the chlorine molecule. Second step is the electrophile attack on the toluene, that is benzene, over which the CH3 is attached. So when electrophile, that is Cl positive, attacks on this electron rich benzene ring, it will replace one of the hydrogen of the benzene ring. Hydrogen ion will be replaced by the Cl positive, and you will get this compounds, that is either this or this. Okay, so your carbocation formation happens. So you can see that chlorine will attack on ortho position. Okay, so this electrophile will attack on the ortho position, replaces one of the hydrogen, and this double bond will breaks, and here at this carbon there comes a positive charge. Okay, this is when the chlorine attacks on the ortho position. When the chlorine attacks at the para position, you will get this compound where chlorine is replacing the para hydrogen, hydrogen attaching with the para carbon. So chlorine is replacing that hydrogen and attaching at the para position of the benzene ring, and this double bond is breaking, and this carbon is getting a positive charge. So you are getting a carbocation. right? Then the third step includes the stability of this carbocation by the resonance. So you get this molecule where the chlorine is attached at the ortho position, right? We are taking a case where chlorine is attaching at the ortho position. Now what will happen? This hydrogen will be removed, okay, because we want our benzene ring to be stable. So this hydrogen, after the donation of these bonding electron pairs to this carbon, for the stabilization of the ring, it will be removed from here, and this carbocation, after the reaction with FeCl4 negative, giving us ortho substituted chlorotoluene. So at the ortho position, after the stability of this carbocation, you will get orthochlorotoluene as your product, where at the ortho position we have chlorine, and at the first carbon we have CH3, okay, plus HCl and FeCl3 are your byproducts in this process. So FeCl3, you can see you are getting at the end of the reaction. So this is the catalyst which is not utilizing in your overall reaction. We are getting it back after the reaction completion, right? And similar step is followed in the para substituted chlorine, okay, or you can say when the chlorine is attacking on the para carbon, then you are getting this carbocation. Now after the stability of this carbocation and with the reaction with FeCl4 negative, you will get your product as para-chlorotoluene, okay. So this is how you will get the ortho and para substituted halogen compounds as your major products after the reaction of toluene with the halogen molecule. So this is how this reactions occurs in the three major steps: the formation of electrophile, the attack of electrophile on the toluene molecule, and then the stabilization of this carbocation after the reaction with the FeCl4 negative and giving us or getting us ortho and para substituted major compounds. Okay, so this is the three major steps including, and this reaction is happening via electrophilic substitution reaction. Let's see our next question. The question, exemplar question number 6. Question is, which reagent will you use for the following reaction? So we have given a reaction CH3, CH2, CH2, CH3, that is a butane. Now this butane is giving us CH3, CH2, 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 Cl plus CH3, CH2, CHCl, CH3. So one is 1-chlorobutane and the other product is 2-chlorobutane. So from the butane you are getting 1-chlorobutane and 2-chlorobutane in this reaction. You have to tell that which reagent you have to use for this reaction. Okay, the options are chlorine along with the UV light, sodium chloride plus sulfuric acid, chlorine gas in the dark condition, or chlorine gas in the presence of iron in the dark condition. So you have given these reagents or conditions. You have to tell that which is the suitable reagent for the given reaction. Okay, so for this question, the correct answer is option A. That is chlorine molecule in presence of the UV light. So we have this given reaction of the butane giving us 1-chlorobutane and 2-chlorobutane. So this reaction proceeds via free radical mechanism. So your butane reacts with the chlorine molecule in presence of the UV light, give you 1-chlorobutane and 2-chlorobutane. That means chlorine attaching with the very first carbon, and in the second compound the chlorine attaching with the very second carbon. Now this reaction involves the replacement of primary and the secondary hydrogen of alkanes by the chlorine atom. Okay, so what will happen that in this butane molecule, the primary hydrogen, that means the hydrogen which is present at very terminal carbon, and the secondary hydrogen, that means the hydrogen that is attaching with this second number of carbon. Okay, this also can count in the second number of carbon if you go from left to right. So these two center carbons containing secondary hydrogens, the terminal carbons containing primary hydrogens. So the replacement of primary and secondary hydrogen of alkanes by the chlorine atoms gives us the product 1-chlorobutane and 2-chlorobutane after the reaction of butane with the chlorine molecule. Light is absorbed by the chlorine molecule and activated chlorine initiates the reaction. So we are needing a UV light condition for this reaction to happen. Why? Because light is absorbing by the chlorine molecule here, the halogen molecule, and this light after the chlorine molecule will absorb this light, they will activate. Okay, they will get activated and initiates the reaction. So step 1 of this process, so for this reaction which is following the free radical mechanism, the step 1 includes the chain initiation process. So we have first of all a chlorine molecule, right? Now chlorine molecule containing two chlorine atoms binding with each other. Now when you pass a UV light through it, they will get activated and dissociate into two free radicals. So you will get two chlorine free radicals from this reaction. The step 2 includes chain propagation. So chain initiation means the reaction is starting. Okay, chain propagation means the reaction is carrying on. So step 2 includes the chlorine radical attack on the N-butane, your reagent, your reactant, right? So when the chlorine radical attacks on this N-butane, you will get N-butyl radical, CH3, CH2, CH2, CH2 dot. So this is N-butyl radical, that is alkyl radical you will get in this process, plus hydrogen chloride will be your side product. Okay, so in the first step, in the chain initiation step, you are dissociating this chlorine molecule into two free radicals of the chlorine, and in the chain propagation step, this chlorine, one of the chlorine radical is attacking on the alkane and giving us alkyl free radical. Then the rest, you can say chlorine free radical attacking on the alkane in a other way and giving you a secondary butyl radical. Okay, plus HCl will be your side product, because as you can see in this reaction, you are getting two kind of products. The one is where primary hydrogen is replaced by the chlorine, the other is where the chlorine replaces the secondary hydrogen from the butyl, right? So when the chlorine radical attack on this alkane and replaces the terminal hydrogen or primary hydrogen, it will give us N-butyl radical. And when the other chlorine radical attacks on the same molecule of N-butane at the second, you can say secondary carbon, okay, then what will happen? You will get a secondary butyl radical after the replacement of or after the elimination of secondary hydrogen from the butyl group or butane. Okay, and this step also includes the side product HCl formation. So this is how you are getting N-butyl radical and secondary butyl radical for this chain propagation. Third step includes chain termination. Now your every product is going to made up in this process, in this step. So your N-butyl radical which you have got after the chlorine radical attacking on your first carbon, you are getting N-butyl radical, and then this N-butyl radical again combining with the chlorine radical to give us 1-chlorobutane as the major product. And in the other way, this chlorine radical again is joining with this secondary butyl radical, and you are getting a 2-chlorobutane as your major product. And the remaining chlorine radicals will combine together So there are two chances only, right? Because we are getting n-butyl radical and secondary butyl radical, two types of radicals in the chain propagation step. So chlorine radical will attack on both the radicals and you will get 1-chlorobutane and 2-chlorobutane both as your products. Now the remaining chlorine radical, the second option is that chlorine radical will attack on the chlorine radical and become a chlorine molecule, right? So the remaining chlorine radical will combine together and gives us the chlorine molecule. So now let's see the explanation of the incorrect options, that why we didn't choose the other options as the correct reagent. We have only chosen the chlorine molecule in presence of UV light, not the other one. Why? So the B option was sodium chloride plus sulfuric acid reagent. So this is not the correct reagent because this combination typically produces hydrogen chloride gas and sodium sulfate. So the chlorine that you need to attack on this butane is going to make the bond with this hydrogen from the sulfuric acid and form the product hydrogen chloride gas. Okay, and the other product you will get is sodium sulfate from this reagent. So the chlorine will not participate in the reaction with the butane. So we didn't use this reagent. The C option was chlorine gas in the dark condition. So here chlorine gas is present, right? It can participate with the butane, but we didn't use this as a reagent in this conversion because chlorination of alkanes, specifically this is very important, chlorination of alkanes requires the presence of light, that is UV light, for the activation of the chlorine molecules for the initiation of the reaction. Okay, either the presence of light or high temperature to initiate the reaction. And if you talk about aryls, okay, or arenes, there you use dark condition. Okay, you don't use light condition, or you don't need any presence of light or high temperature. That reaction happens in the dark, the halogenation of the arenes. But in the alkanes case, if you are doing the chlorination of alkanes, then you are requiring the presence of light or high temperature for the activation of your chlorine molecule to initiate the reaction via free radical mechanism. So in the dark condition, what happened? Chlorine molecules do not dissociate into reactive chlorine radicals and the reaction will not initiate. The last D option was chlorine gas in presence of iron in the dark. Now we have added another more catalyst that if chlorine gas can't react, or if chlorine gas in the dark condition is not suitable reagent, then let's provide one more catalyst, that is iron. But still this is not the suitable reagent for the conversion of butane to 1-chlorobutane and 2-chlorobutane. Why? Because in the dark condition, even if the iron is present as a other catalyst, the necessary radicals will not form and the reaction will not proceed. Okay, so this dark condition we don't need. We need UV light, the presence of light or high temperature for the reaction to proceed. So that's why your correct answer is A option, that is the chlorine gas along with the UV light presence. Okay, let's see this question, the Exemplar question number 9. The question is, in which of the following molecules carbon atom which is marked with asterisk, that is star, is asymmetric? So we have given 4 different molecules, you can see, and in these 4 molecules, the carbon, one of the carbon is marked with this star, this asterisk sign, right? You have to tell that in which of the following molecules the carbon is asymmetric. So options are first, second, third and fourth, first, second and third, second, third and fourth, or first, third and fourth. You can see your first molecule where carbon having asterisk symbol attaching with hydrogen, iodine, bromine and chlorine. The second molecule where carbon having asterisk attaching with deuterium, iodine, bromine and chlorine, all the different atoms, right? In the third molecule, this asterisk containing carbon attaching with hydrogen, hydroxyl group, methyl group and ethyl group. Now lastly, in the fourth molecule, this asterisk containing carbon attaching with 2 hydrogen, one methyl and one ethyl group. Okay, so now after looking at each of these 4 molecules, you have to tell which carbon is asymmetric, which molecule have asymmetric carbon. Okay, so for this question, your correct answer is option B, that is first, second, and third. That means first molecule, second molecule, and third molecule. So, first of all, let's understand the concept of asymmetric carbon or chiral carbon. So, asymmetric carbon, also known as chiral carbon atom, and a carbon atom having all of its 4 valencies with 4 different groups or atoms. So when the carbon is having all of its 4 valencies with the 4 different groups or atoms, then it is considered as asymmetric or chiral carbon. Okay, that means the carbon have tetravalency, you all know. Okay, and each valency is occupied by 4 different group of atoms. Then that carbon is asymmetric, or you can say that carbon is chiral carbon. If you see the compound first, second, and third, so carbon satisfying all of its valencies with 4 different groups in these molecules. You can see in the first molecule, we have carbon connecting with hydrogen, chlorine, bromine, and iodine. All the 4 are different. In the second molecule, also carbon connecting with deuterium, iodine, bromine, and chlorine. In the third molecule also, the carbon is connecting with hydrogen, hydroxyl, ethyl, and methyl. All are different groups, right? So all of its valencies are occupying by 4 different groups in the first, second, and the third molecule. Carbon in the compound first, second, and third is hence asymmetric. If you look at compound fourth, the carbon satisfying 2 of its valencies with 2 hydrogen atoms, that is, we have presence of similar atoms. So you can see this fourth molecule where carbon is attaching with hydrogen and again hydrogen. So 2 similar atoms are present in this compound, right? Now this means that the carbon in the compound fourth is not asymmetric or not chiral. That's why our correct answer is option B, that is only first, second, and third molecules containing carbon which is asymmetric in nature. Let's see our next question, Exemplar question 13. Question is, chlorobenzene is formed by the reaction of chlorine with the benzene in the presence of AlCl3. Which of the following species attacks the benzene ring in this reaction? What you have to do, you have given that the chlorobenzene formed when you react the chlorine molecule with the benzene ring in presence of a particular reagent AlCl3. You have to tell that in the given following species which will attack the benzene ring in this reaction, in the formation of chlorobenzene reaction. The options are Cl-, Cl+, AlCl3 or AlCl4 negative. So for this question, your correct answer is option B, that is Cl positive. Cl positive is a species that is going to attack on the benzene ring in this reaction of formation of chlorobenzene. We have given that this reaction happens in the presence of AlCl3 catalyst. Now AlCl3 catalyst will act as a Lewis acid. Also, it will activate the chlorine molecule to show the heterolytic cleavage, and it is an electron deficient molecule because, as we mentioned, that it will act as an Lewis acid. So it will form, the AlCl3 will form AlCl4 minus and the chlorine plus Cl plus, which reacts with Cl2. When reacts with Cl2. So AlCl3 when reacts with the chlorine molecule, because we are doing the chlorination of benzene ring, right? So that chlorine molecule when reacts with the AlCl3 catalyst, you will get AlCl4 minus and Cl plus. Cl plus here is going to be present as an electrophile. So AlCl3 will react with the chlorine molecule. You will get AlCl4 minus plus Cl plus. Cl plus is an electrophile here. So Cl plus is an electrophile. It will attack on the electron-rich benzene ring to give us the chlorobenzene as the major product. So after the formation of electrophile by the reaction of chlorine molecule with the catalyst AlCl3, you will get electrophile Cl positive. Now the Cl positive will attack on this electron-rich benzene ring because your AlCl3 is a Lewis acid, electron deficient molecule, and it will produce electrophile. Electrophile attack on the electron-rich benzene ring and gives us the major product as chlorobenzene. Okay, so which species is attacking on the benzene ring? Our electrophile Cl positive. Hence our correct answer is option B. Let's see our next question. Exemplar question 17. Question is, which of the following alkyl halides will undergo the SN1 reaction most readily? We have discussed this kind of question a lot more time in the previous lectures too. So SN1 reaction, substitution nucleophilic unimolecular reaction, right? From the given options, you have to identify the alkyl halide which will undergo the SN1 reaction mechanism faster, most readily. The options are CH3 whole thrice CF, CH3 whole thrice CCl, CH3 whole thrice CBr, or CH3 whole thrice Ci. Try to observe the relationship between these different alkyl halides given. What is same, what is different, okay, and what actually we focus on while looking at the reaction rate of SN1 mechanism. Then you can answer this question. So you have given some time. Try to solve this question and then we will see the answer. Okay, let's see. So for this reaction, for this question, your correct answer is option D. That is CH3 whole thrice Ci. Now in the given options, all of the given compounds having same alkyl group, that is CH3 whole thrice C. You can observe, right, that in each of these alkyl halides, this alkyl group with which the halogen is connected, in each of the options the alkyl group is same, CH3 whole thrice C, which is a tertiary, you can say, alkyl group, right? SN1 reaction for same alkyl group. Now if we have the molecules having same alkyl group but the leaving group are different, the halide ions are different, then the SN1 reaction will be the SN1 reaction rate will depend upon the nature of leaving group. So if you have the same alkyl group, you will focus on the nature of leaving group. So rate will be faster in the molecules having the better leaving group. Okay, the molecules having better leaving group because it can without the need of any much efforts, it can better leave from the reaction or from the molecule left behind the carbocation, and then your incoming nucleophile can easily attack on the carbocation to form the product, right? So rate will be faster for those molecules which is having better leaving group. And if your halide ion size is larger that means it will be the better living group. That means the reaction rate will be larger too, right? So the reason behind this fact is that with the increase in the size, if you go down the group in the halogen group from fluorine to iodine, the size increases, right? And with the increase of the size of halide, the bond it is forming with the carbon in the alkyl halide becomes weak. That means it will be easy to break that bond. So that's why it will be serving as a better living group with the increase of the size. That means the rate of reaction will be highest for alkyl iodide, then for alkyl bromide, then for alkyl chloride, and least will be for alkyl fluoride. Okay, so this is the case that because iodine, from all of the halogen, iodine will be having the largest size. So iodide ion will be the largest size halide ion. So it will be a better living group. So reaction rate will be faster in the case of alkyl iodide. So the rate of reaction order in these given alkyl halides are as like this: highest for alkyl iodide, least for alkyl fluoride. So iodine is a better living group due to its large size among the given compounds, and the CH3 whole thrice Ci, this will give the SN1 reaction most readily. Because if you have same alkyl group, then you focus on the living group in the SN1 reaction, right? SN1, if you remember, SN1 reaction happens in the two steps. The first step is the slowest step, a rate determining step, and it includes the formation of carbocation. If your carbocation is stable, then your reactivity will be larger. But that is in the case of when your alkyl groups are different. Here, in this case, in this question, your alkyl groups are same. Then you look at the better living group. If you have the better living group in the molecule, then its reactivity will be faster. The rate of reaction will be faster with that molecule, right? So CH3 whole thrice Ci will gives the SN1 reaction most faster, most readily, and your this alkyl fluoride will gives the SN1 reaction least readily, least reactive. So your order of SN1 reaction, finally you can write it as highest for this CH3 whole thrice Ci, then for CH3 whole thrice CBr, then for chloroalkyl, and then least is for fluoroalkyl. Okay, so which of the alkyl halide will undergo SN1 reaction most faster? Your correct option is D, that is iodoalkyl group, iodoalkyl molecule. Let's see our next question, the exemplar question number 25. So this question is saying that which of the following compounds will give racemic mixture on the nucleophilic substitution by hydroxyl ion? So we have given three different molecules or the compounds. You have to tell that which compound will give racemic mixture when you do its nucleophilic substitution with hydroxyl ion. The first molecule is CH3CH C2H5Br. Second molecule CH3C Br C2H5 CH3. Third molecule CH3CH C2H5 CH2Br. Now, if you are able to find the difference between these three molecules, then you can easily depict that which compound will give the racemic mixture on the nucleophilic substitution. The options are second compound, first, second and third compound, second and third compound, or first and third compound. So for this question, your correct answer is option A, that is the second compound. Only second compound will give racemic mixture on the nucleophilic substitution reaction. So let's first of all understand the racemic mixture. name has mixture. Okay, so this mixture actually contains the equimolar mixture of the enantiomers. Racemic mixture is a mixture containing two enantiomers in the equimolar amount, that is 50:50 ratio. And racemic mixture has zero optical rotation. Why? Because one enantiomer will cancel out the optical rotation of the another enantiomer, and the overall optical rotation of racemic mixture will be 0, because those two enantiomers are present in the equimolar amount, so the optical rotation will cancel out. This reaction will proceed via SN1 mechanism and will give racemic mixture. So this is the concept given, that in the SN1 mechanism we obtain racemic mixture. Okay, so the reaction proceeds via SN1 mechanism. The substitution nucleophilic unimolecular mechanism gives us racemic mixture of the products. Now we will see that the SN1 reaction happens in which case, and what is the rate of the order or rate of the reactivity with which compound. So in the SN1 reaction, the reaction will proceed via formation of carbocation, right? Because the first step includes the formation of carbocation. The second step includes the attack of nucleophile on the carbocation. So here in the SN1 reaction, stability of the carbocation is the key factor. So more stable the carbocation, more will be the rate of your reaction. So rate of reaction you can write as highest for tertiary alkyl halide, because it will provide you tertiary carbocation which is most stable. Then for secondary alkyl halide, and the least reaction rate is for primary alkyl halide, because it will give you a primary carbocation which is least stable. So compound which is given in our options, which is actually given in the second part. Okay, so like this one, this is actually a tertiary carbocation, or you can say tertiary alkyl halide, which will follow the SN1 mechanism to react via nucleophilic substitution reaction. Okay, if you observe the second compound given, the bromine is present on this carbon which is attaching with other 3 carbons, right? So this is a tertiary alkyl halide. It is going to provide us a tertiary carbocation, the most stable one, and because stability of carbocation is a key factor in the SN1 reaction, the second compound will follow the SN1 mechanism. So our correct option is A, because the question asked was that which compound will give racemic mixture. So our second compound will follow the SN1 mechanism reaction for the nucleophilic substitution, because it will going to gives us a tertiary carbocation. So our correct option is A option. So let's see the next question, Exemplar question number 30. Question is, which is the correct increasing order of boiling points of following compounds? We have given 4 different compounds. You have to tell the correct increasing order of boiling points of them. Compounds are 1 iodobutane, 1 bromobutane, 1 chlorobutane, or butane. So the options are, for the order of boiling points, increasing order of boiling points, highest boiling point for 1 iodobutane, then 1 bromobutane, then 1 chlorobutane, and least is for butane. Or highest is for butane, then for 1 chlorobutane, then for 1 bromobutane, and the least is for 1 iodobutane. Or highest boiling point is of 1 chlorobutane, then 1 bromobutane, then 1 iodobutane, then butane. Or the highest boiling point is for 1 bromobutane, then 1 iodobutane, then 1 chlorobutane, and the least is for butane. So for this question, the correct answer is option A, that the highest boiling point will be for 1 iodobutane, then for 1 bromobutane, then for 1 chlorobutane, and the least is for butane. Why? So boiling point, actually we have covered the boiling point, right? So boiling point increases with the increase of molecular mass of the halogen atom. Okay, if your halogen atom has greater atomic mass, then its boiling point will also greater. So also the boiling point affected by the increase of surface area. The boiling point increases with the increase in the surface area of the molecule. If you see the atomic mass of halogen atom, you can see that iodine will be having the highest atomic mass, then bromine, and the chlorine will have least atomic mass. We are only considering, or we are only seeing the order of atomic mass of chlorine, bromine, and iodine, because only chlorine, bromine, and iodine are the halogens which are present in our given compounds: iodobutane, bromobutane, and chlorobutane, right? So if you compare their atomic mass for these halogen atoms, highest is for iodine and least is for chlorine. So butane doesn't contain any halogens, so therefore it will be having lowest boiling point comparative to other alkyl halide given, because they are containing halogen plus the carbon hydrogen compound, that is butane, right? But if you have only carbon hydrogen compound, that is butane, and doesn't contain any halogen, then comparatively it is going to have lowest atomic or molecular mass, that means lowest boiling point. So atomic mass of iodine is highest, so boiling point of one iodobutane molecule will be maximum among all the given compounds, and the correct option will be the A option. That is this order of the boiling point: highest for one iodobutane, then for one bromobutane, then for one chlorobutane, and the least is for butane. Let's see our next question, exemplar question 33. Question is, which of the following statements are correct about this reaction? So we have given a picture of this reaction where the first is hydroxyl ion, which is nucleophile air. Second is this methyl chloride. Third is this transition state representation. Fourth is our final product, which is an alcohol, methanol. And fifth is this chloride ion, leaving group. From the options, you have to select the correct statement about this given reaction. Options are: the given reaction follows SN2 mechanism. Second and fourth have opposite configuration. Second and fourth have same configuration. Or the given reaction follows SN1 mechanism. So for this question, the correct statement is present in our option A and option B. So if you see the given reaction, it will be the hydroxyl ion nucleophile attacking on this halogen, or you can say haloalkane, that is chloromethane. Okay, so you can see this configuration. So this chlorine is attaching with this carbon, and the hydroxyl ion, which is nucleophile, will attack on this carbon from the opposite side of carbon-chlorine bond, and you will get this transition state of the compound where the carbon is attaching with 5 different, or you can say carbon is forming 5 bond at the same time, right? And you are getting your final product after the removal or after the breaking of the carbon-chlorine bond and the formation of hydroxyl and carbon bond. You are getting the final product as methanol plus chloride ion as a leaving group will be left from the reaction. This is the given reaction. Here the first is hydroxyl ion, which is acting as a nucleophile attacking on the haloalkane, right? So nucleophile first will attacks the carbon present in the second at 180 degree to the leaving group. Leaving group here is chlorine. Okay, 180 degree means from the opposite side of carbon-chlorine bond. So nucleophile attacks on the carbon present in the second compound at 180 degree to the leaving group. You can see that in the third, that is transition state, that the bond angle between the OH carbon Cl is 180 degree, right? That's why we are writing that nucleophile attack the carbon in the second at 180 degree to leaving group. Now the reactant second, that is your chloromethyl. Now this reactant and the product fourth you are getting, that is methanol, have opposite configuration. You can clearly see that because it happens because nucleophile attack from the opposite side of the carbon chlorine bond. So the configuration reverse and you will get a opposite configuration of product from the reactant. A transition state is observed in which the one bond is broken between carbon and chlorine and one bond is formed between carbon and hydroxyl group simultaneously. That is in the one single step. That's why we are calling it as a transition state, unstable. Also, this reaction is following SN2 mechanism, substitution nucleophilic biomolecular mechanism, and only happening in single step. So your option A, that is the given reaction follow SN2 mechanism, is the correct statement, and your option B, that second and the fourth, reactant second and product fourth have opposite configuration, this is statement which is also correct. So our correct answer is option A and option B both. Let's see the next question. The Exemplar question 34, which asks that which of the following statements are correct about the reaction intermediate. So again we have given this similar reaction. The intermediate is also similar, your reactant is also similar, your nucleophile is your hydroxyl ion, the leaving group is chloride ion, and you are getting the product as methanol. You have to tell the correct statement regarding the intermediate. The options are: intermediate third is unstable because in this the carbon is attached to 5 atoms. Intermediate third is unstable because carbon atom is sp2 hybridized. Intermediate third is stable because carbon atom is sp2 hybridized. Or intermediate third is less stable than the reactant second. So for this question, the correct answer, or you can say the correct statement containing options are A and D both. So OH minus here, that is first, will act as a nucleophile. The hydroxyl ion is a nucleophile, and the nucleophile attack on the carbon in the second reactant at 180 degree to the leaving group, that is chlorine. The reactant second and the product fourth, that is methanol, you are getting have opposite configuration due to the attack of nucleophile on the carbon from the opposite side of carbon chlorine bond. And a transition state, which you are calling here in this question as intermediate, is observed in which the one bond is broken between carbon and chlorine because chlorine is a leaving group, and one bond is forming between hydroxyl and the carbon simultaneously in the single step. Hence, this reaction, given reaction, will follow SN2 mechanism. The intermediate third you are getting in this reaction represents a transition state which is unstable. So this is highly unstable, and the carbon atom in this transition state is sp2 hybridized because it is partially bonded to two nucleophiles at the same time, chloride and the hydroxyl ion. And also it is lesser stable than the reactant second, that is methyl chloride. And your reactant second, that is methyl chloride, carbon atom is sp3 hybridized in the methyl chloride, and also it is more stable than the intermediate. The intermediate highly stable due to the presence of this 5 bonds forming by a single carbon at the same time. So your option A statement, that intermediate third is unstable because in this the carbon is attached to 5 atoms, is the correct statement. And your option D, that intermediate third is less stable then the reactant second is also the correct. So our options A and D both are our correct answer. Okay. Thank you so much. That's all for today's chemistry session. Thank you.